Okay, we can get started. Shortly about myself and the company before jumping into the actual topic. Myself, Parthiban, and I'm part of the company called Linumis, which does embedded software servicing. And I've been into embedded software for like maybe 13 plus years now, working with multiple domains, primarily in Linux in the starting days. But now, let's say 5 years in the past, we started with Zephyr as well. So I myself primarily live in Berlin. So this is in short as a portfolio of what we do in Linumis. Let's say embedded Linux, Zephyr RTOS consulting for the embedded software itself, security, and whatnot. You can think of like an just a service company. We don't do hardware and backend and other stuff, but just embedded software stuff primarily. And as part of it, like Zephyr is our portfolio, and we speak about it now today. And just before we get started, like how many of you in one way or another used Zephyr or programmed Zephyr? Okay, that's at least like 3/4 of the room. That's great. So nice. So I mean, this presentation is not super long. It's a shorter one. Please interrupt me if you have questions immediately. There is no problem. So as part of our portfolio customer requirement, we started working with Texas Instruments SoC, which is MSP M0 series, which is launched like 3 years before, and we are currently like working closely with the Texas Instruments and upstreaming Zephyr support for MSP M0. And we are aware of this particular SoC being launched in March, let's say in this year, which is like a super smaller one, and which runs at like 24 megahertz, and which contains like 1 kilobytes of RAM. And as with our upstreaming effort, we already completed all the other portions. For example, clock support, driver support, and SoC support for the other series of MSPM0, but not for this particular series. So it coincides that like we started with, let's say, this chip appeared, and then why not? We have all the other things ready. Let's say driver landscape is ready, Hall is ready, and everything is ready. Why not try Zephyr with, let's say, a super minimalistic version of this? And quickly, I mean, I didn't have the presentation for this, like slide for this, but quickly I grabbed into the Zephyr tree when this appeared. The smallest RAM which Zephyr runs today is on 2 kilobytes, which is from ST, and that is like, let's call, there is like a basic minimalistic support like clock, serial, and once you enable basics of this, then your RAM is gone. Let's say it's already full. You cannot do anything with this. Like say probably you can blink an LED and do a hello world in a loop and play around. Okay, so why not under 1 kilobyte and see if it is really usable, because probably that is where the idea of this microcontroller comes in place. Let's say replacing 8-bit and 16-bit is like impossible still, but probably that's the idea of Texas Instruments, to have something in that placeholder in the lowest compatibility. So we managed to run, let's say, good amount of functionality with Zephyr in this particular smallest microcontroller. So that's the main idea of this presentation also. So as I said, this presentation is not going to be long. It is super simple one. So please stop me. Firstly, when you compile Zephyr as a for any particular SoC, any particular project, it is going to give you one single final file, which is bin file or X file, which is going to dump into your flash region. So it's a flat memory. Altogether, it's one single image. It's a flat memory. You can consider like a one single process it's going to run in your MCU or whatever microcontroller you're trying to do. So this means when you kickstart your SoC, the first thing which does is from the vector table is copying the whole data section from the flash into the RAM. So this section belongs to, let's say, the global data which you declare all around any form of threads. You can call your thread as main thread or application thread or TCP/IP thread or whatsoever. Any thread, any form of global variable, or in fact your application logic, any form of global variable is copied right in the beginning of your initialization of the Zephyr. So when you do it, that's gone for real. Roll for real by meaning it's gone for all the time during the execution of the phase. So that's done. Meaning, so as long as you keep your data section super smaller, you have larger amount of memory to play around for the real functionality. So then why not text is not copied? So when you have text copied into the actual RAM, then eventually you do not have RAM at all to work in real world. So how does microcontroller of this kind works? All of them works with execute in place, meaning the CPU will eventually fetch the instructions directly from the text section, living in the flash and execute directly in the CPU. And the remaining part is what we realistically care when there is realistically a super minimalistic RAM. Say, for example, what goes into the RAM, you can call like data section goes into the RAM, but what other things can go? Let's say if you create a thread and call a function, your function's prologue and epilogue goes to the RAM. Prologue by means like from where your function is called and where or the arguments are, and when you wanted to return, the epilogue portion needs to go back to the real world. I mean, from where you are actually coming from. So those portions needs to go into the stack, or those are the portions which you realistically care about the RAM. So in a nutshell, if you declare a global variable, that's gone for real. So that's in a nutshell. So simple overview about how you can do with multithreading and without multithreading for Zephyr booting. Let's say when you give a power to the SOC, the ROM kickstarts the reset vector, just the base word, I mean the 4th byte offset. The first 4 bytes you have the stack pointer where you allocate the basic stacks for initialization, do some magics. I mean, during the initialization phase, you use this particular stack until you set up a real thread to do some magics. So the reset handler will be kicking in, and it will initialize probably the NMI interrupts if there is an exception during the initialization. So some basic vector tables initialization will be done in the reset side, and then immediately we jump into the C code. So when I say C code, that's the first portion of C code which would be executed. I can show if there is time in the chat. But once in the C code, what exactly it does, it is all, I mean, the whole portion which I'm showing is all architecture dependent. So every architecture has its own way of booting. Reset handler is the default one eventually, but most predominantly we are speaking about ARM here. So the C code enters, and from there we are basically copying. When I say copying, this is what I meant. So copying the whole data section from your flash to the RAM, and that would be initialization of the BSS section to set it as 0 and do real copying, and then it would jump into the architecture independent code. That is when you have a differentiation between what is with multithreading and without multithreading. So without multithreading, there is some form of initialization would happen. Let's say how your drivers needs to be initialized in sequence and how other things would happen, which is same for both. And without multithreading, it would just straight jump into the main code. And if you have a tight while and doing some sequential magical logic, that would be the case. And with multi-threading with Zephyr, you have 3 different threads which is forked, you can call, or branched, you can call. So what are all this? But what exactly this is doing? Like, and there is no activity in the CPU. There is an idle thread which does nothing but just put the CPU into idle sleep state. So whatever the sleep power management support which is given by the SOC. So MSP0 provides one form of it, and ST provides a completely different idle procedures it provides. Say this is an ideal thread which needs to be scheduled by the scheduler when there is no activity needs to be done. And this is like the last piece which would be started by your, this is where your main function is called. Obviously the actual functionality which will be called. From there you probably create additional threads, multiple other functionality which needs to be initialized. So there is also one other portion called dummy thread. So you might question, why do we need a dummy thread? But this is how it is defined at this point of time. We are trying to change all these pieces now in the core portion of the kernel because of the memory limitations which we are going to speak now. So what this does is gives some information to the scheduler, that is like there is a pre-existing thread which does nothing, but from there it can actually schedule a real thread. So it sets up a minimalistic skeleton thread without any entry point function, without doing anything, but just gives a space holder to either schedule an idle thread or real thread, or the other threads if you realistically created in the main function. So this is all 3 things which would be done during the initialization. There are plenty of other things which are done. Let's say, for example, it will initialize multiple drivers, application init calls, and so on. But that's not the context of this discussion, so I haven't placed all of them here. Now that's what we're going to speak now. For life free, yeah. So yeah, that's like I called it a 3 different threads, right? So main thread, dummy thread, and then idle thread. So I'm not sure how many of you can see in the screen these values, but these all belongs to BSS sections, right? So when I first compiled, at least for this, but until this SOC, I haven't never noticed, because we had a luxury life, as most of you had already having, let's say 24 kilobytes of RAM or 34 or 512 kilobytes of RAM. Why one should care about every single bytes of the memory? But when it comes to under 1 kilobytes of RAM, you have to think where the memory goes in every single bits. Say, then when I figured out, I mean, this is like compilation not for that particular SOC which I meant for 1 kilobyte, but generally, okay, you can consume. So there is like 112, 112, 112 repetition for 3 different threads. This is because threads are statically defined, and this thread structure is basically a global variable all across Zephyr. When you create a thread and define a stack for it, and this is not stack, but instead kernel wants to maintain the metadata about your thread and about what has been done in the architecture level, what is needs to be known for the scheduler, and this is just the metadata. 3 cross 112, 336 bytes gone. So 1 kilobytes of RAM, 1024 bytes, out of which like we lost like almost 336 bytes without doing anything. Let's say all this is literally not my ideal expectation. Let's say dummy thread, I don't know why I realistically need it. Ideal thread, probably I need it, but if I am really worried about ideal, then I am really worried about it. So how about removing ideal and also dummy, care only about main thread. So that's when like this is the point we figured out. Let's say we need to find where all the memory goes and how much amount of memory goes. Go on, go on, go on.
So which all are text and which all are data?
There is no text sections here. This is all RAM report. But I'm not sure if you are, how many of you are aware of RAM reporting from Zephyr? Not much. Okay, let's try. If you cannot see the screen, let me know. My laptop is kind of slow. I will try. Is the screen visible? I'll try to zoom in. Okay, so this is just the static RAM reporting methodology. You can call like with whatever the T option. You can, there are multiple other options to T you can specify, but for looking at the RAM usage, this is what I pointed out in the presentation as well. So 112, and you might not observe other dummy and stuff here because we killed all the other stuff to make it workable for this particular SOC. But what you see here is nothing related to text section. So nothing related to text section comes to here. No, it is just the instructions which is part of text sections. When the CPU fetches, executes it, when you have a variable to say store an int a is equal to whatever, then this a is equal to whatever goes to the stack. That is the part of stack, but not the instruction. Instruction goes to the CPU and executes, and the output is going to store into the stack, not the instructions itself.
Okay, but when you build, why you have something the 1K, 2K, and
here, okay, so this is all the other values which you are pointing out, right? Let's say 124, 2048. These all the stacks. Okay, so this is the main stack, this is the interrupt stack, this is the idle thread stack. So when I say main thread stack, this is when you call your main function, let's say print hello world, and where does this stack frame setup for print k. Calling the print k is eventually meaning there will be a prologue jumping into print k function, and then coming back means epilogue, right? So what exactly print k does, probably it is going to call a libc function called vf printf blah blah whatever, right? So those needs to run somewhere, meaning the prologue, epilogue, and what are the local variables it's part of it, that needs to be stored somewhere. So these all default stack sizes for main, interrupt, and idle thread. So main is what I explained now. Interrupt is means like say you get a I2C interrupt as a response from I2C controller, then the function in the interrupt handler, ISR you call it, right? So where does it run? Where does the local variable of those will go? That is where the interrupt stack is belonging to. And then the idle thread I can show, but then like the simplest example would be when CPU has nothing to do, then it will jump into the idle thread doing nothing. For that, it needs a stack. Does that answer a question?
but that size, that size is bigger than your.
I mean, this is default compilation of, let's say, Zephyr. Default compilation of Zephyr without any optimization done.
But it is not built for this particular device.
Yeah, it's not for that. Like I'm just showing as an example here. My set is different than the actual value which you can see right now on the live screen. But yeah, yeah. I mean, those are the different sizes here. So speaking about that, I mean, don't need to be sorry. You just interrupt me anytime. That's fine. Okay. So the next thing is when we figured out this is the amount of memory which is consumed in a nutshell, and then this eventually provoked trying to figure what is the default size of compiling a hello world in a supported SoC or supported board. So then that comes to, let's say, 4 and at least 12% under the 32 kilobytes of RAM. This is taken for another Texas Instruments SoC, which is like not yet in the upstream, but it would be upstream in like a couple of weeks now. So that is like around 4K or 4.2K you can call, right? So then we have to split where this 4.2K goes. Then let's see what are all the drivers currently been enabled. This is the default compilation. I didn't change anything. So let's say the drivers portion altogether combined together takes like 380 to 1 bytes, and the most culprit is here is like 335 on the GPIO, right? So this is just a basic summary report. And then when you look at each and every byte, you need to look at why DSS and what portion goes to the global data section and so on and so forth. And the real kernel itself is smaller. I mean, like this is without any optimization, not aggressive, nothing, anything like so. This is very basic kernel without anything. Like there is like 14 bytes. When you do some aggressive optimizations like GCC, OZ or OS in terms of size optimization usages, then this will drop somewhere around 180, 160 sizes, 60 bytes. So in a nutshell, you already lost like 380 here and 314 in the kernel, and that's the summation there. So in this case, assume you have a RAM of 1 kilobytes. How do you get into a direction of running Zephyr, let's say, without this much amount of RAM? We do not have 32 kilobytes for sure, and we only have 1 kilobytes. How do you actually go into that particular direction of optimizing Zephyr to fit into 1 kilobytes RAM? I can work every pieces of code, remove unused ones and figure out, but until that point, your compilation is not going to be happy. Anyway, the compilation is not going to be successful. So then the only way to do it is fake it. Fake it by meaning during the compilation phase, tell the compiler, tell the system that we have 2 kilobytes of RAM instead of 1 kilobytes. That's like 800. That is 2 kilobytes RAM. Fake it, and then your CMake system, DTS system, and all the compiler is happy. And but then like with that, we can technically report how much amount of realistically usage, and then you can start optimizing from there. So when we port, let's say the MSP M0CX series or whatever the series in general, what you technically care in first point of nutshell. So you have to see your architecture is supported or not supported. So the first thing, so ARM in this case scenario, ARM M0 plus, so eventually supported. So no worries, tick, that's fine. If your architecture is of this kind of smaller RAM you wanted to support, then if there is no architecture support, then you eventually need to add it there. The first point needs to be done. And the next thing immediately is SOC files with respect to, let's say, if you're already, let's say, yeah, part of Zephyr, then something of this kind. So you might already have, like, say, the directory structure for SOC TI, and then for other SOCs you already might have another directory, and there you can see the CX series already added in this particular image, let's say, yeah, here. So that support needs to be done. So what goes in here is basically initialization of the SOC. For example, your SOC needs some special attention in terms of initializing during the boot up sequence, not just setting a stack pointer and initializing your ARM Cortex is not enough. Probably your SOC has some special case scenario that needs to go in here. So that needs to be done as the first thing. And drivers, when I say drivers, what part of the drivers you need to implement in the first step? So the first thing is timer, GPIO, pin controller, and then clock, and then UART. So without clock, you will not be able to drive UART as an output side. Without GPIO and pin controller, we will not be able to see on the pin, let's say, what is go. If you wanted to see some data on the UART side, you will not be able to see it. And the timer, which I eventually come into the next slide, why, and UART eventually you need, otherwise you will not see anything in the console. So that's the basic thing you will eventually need to go in there. And the point device tree, how many of you from Linux world? Just quick question. Okay, super. So that's 1/2 I would say. Yeah, so you again have a directory structure wherein like the device tree files for the respective SOCs needs to be done, and this defines, let's say, what is the CPU contains and what is the your platform device lives and which address it lives and so on and so forth. So this is like defining all the available or usable set of IP blocks and which address they live in. So that's the next portion. You need to define the device tree, and the last thing is boards TI here, let's say. Yeah. So wherein this board definition gives you, let's say we use a launchpad. You can have a custom PCB and you define the device tree for this and how, what are all the peripherals and what you enable technically. That goes into this particular directory. So once you define these things, you can run basically one simple thing, which is hello world or LED blinking or playing with some GPIOs. So this picture I took it from the Zephyr documentation. So the hierarchical organization from architecture until the board setup. So these all support, and which part of drivers you technically need to get Zephyr running. Wonderful. Just a second. That
HDMI crash.
HDMI crash. Let me see what happens. USB crash. I did X fine now. Let's hope. That is link attached. It should come now. Sorry?
No, it shows the tool-in link detected.
Okay, sorry. Sorry for the glitch. I don't know. Arc Linux behaves somehow. Not a Ubuntu fan. So, okay. So, in there, like, that's the porting set of things which you need technically to get started with that, right? So, yeah. So, then everything is ready. Okay, I prepared everything. I mean, at least I'm happy that like my all my team members, like, we worked in this particular project to get drivers support, SOC support made easier, because it's not just me. So that was quicker. Then, like, the first thing which comes to my mind is like run a hello world and see if it realistically runs. What happened is, when we run hello world, we saw hello world, but then it didn't loop at all. What could happen? Like, there is a sleep function, but it should come after 1 second, but it never happened. So what happened? For some reason, MSP M0 series, all the rest of the series is having sysdig, but this particular series remote sysdig altogether, just to probably to save space, money, or whatsoever. The sysdig itself is removed. So when you do not have sysdig, you don't have interrupt, you don't have sleep, you have the basic functionality broken. So there is no reason of running multi-threaded RTOS in that particular scenario. It's a tight while. It's in the hardware itself. I'm not speaking about the MSP M0 CX series doesn't have sysdig in the SOC socket itself, the IP itself. So the sysdig is gone. It's completely removed. So that was surprising, because we were imagining that like enabled sysdig in the SOC definition and expect the sysdig timer to come on time, but that ISR never hit. So then we figure. Sorry?
What is the expectation? Is there an external timer
That's what we speak now. Okay, that's what we speak now. So then we speak why. Okay, what on an earth will a sysdig would do when it presents in the system, right? What is the role of a sysdig? In a nutshell, it will give an interrupt periodically. Let's say you define a clock cycle frequency on top of it. Every 1,000 cycles creates an interrupt, which is called tick, and then the tick indirectly drives or directly drives the scheduler to look for other set of threads or activities which is present and then wait it. So if it is not present, you cannot sleep, because when you sleep, your thread goes to wait queue and never returns back to ready queue, and then you will have no chance to run it. So the stick is gone, the role of the stick is gone, that means you will not be able to run it. So how do we solve this? So there is timer in part of the MSPM0. Timer is the basic element which existed from, let's say, 40 years now, probably like even from 8051 or even before. Timer is there, at least, happy for that. So we have to implement the timer in a way it does the job of scheduling to help the scheduling algorithm, or let's say provide the other portions of the input. So happy to see that like Zephyr already has this infrastructure where you have to implement these set of functionality to make this any form of timer. It doesn't need to be systic or any form of timer. You can make use of this for scheduling algorithm. So whether you run it at high frequency or low frequency, that is again part of the timer configurations and how fast your timer technically runs. So what are all these functions? I'm not going to detail every inch of these functions, but the most important ones. Say the clock announcement. Clock announcement is basically, let's say, when there is a tick, let's say after 1,000 cycles of your clock or 10,000 cycles of your clock, there will be one tick counted, and this needs to be announced to the scheduler or the operating system itself, and then this tick counts, meaning the background timekeeping of the Linux system would be going forward. So we need to announce the ticks. So whatever the way you get the interrupt, that is part of the hardware, but this functionality needs to get like periodically or non-periodically. So back in days, let's say you can call 15 years, 20 years before, all of the timers are like periodically configured, means like every 1,000 cycles you get a tick, report to the kernel, 1,000 cycles, report to the kernel, and so on. Whether your system is realistically doing something or not realistically doing anything, we still report the ticks. That was done like that. But now it is not the case, because there is a concept called tickless kernel in Zephyr or Linux kernel, you can call tickless kernel, wherein like you don't need to report every single ticks. Instead, let's say when there is no real uh, task for the next 100 milliseconds to be scheduled, the CPU can happily sleep for 100 milliseconds. Then why do you realistically announce the CPU, let's say operating system, that every ticks? So in that case, it pictures, let's say you have to set a timeout functionality, then like say clock set timeout, the scheduler can sleep for this much amount of time, don't report me anything until then. So you have to ask the timer saying, okay, wait, don't hold, don't report me for this much amount of time. So that functionality can be implemented as part of your timer implementation, and then let's say after the expiration, the timer driver needs to take care, like say it sleeps for 10 milliseconds or 100 milliseconds, it needs to know its way, because time needs to be kept. If you sleep for 1 second, let's say your time is like 11:10 and 11:10, 11:11. So then you have to wake at 11:10, 11:12 the next second, not like the same time after you coming out of it. So the timer driver needs to take care of how much delta you actually slept, and then like come again with announcement. So that is called tickless kernel support. So that needs to be done. All the rest, like you can think of like doing power management when it is used and how it is used. Eventually this part needs to be implemented as the core implementation of the driver. So I'm not, as I said, like I do not have all the pieces of the achievements which we done in the presentation. So I will quickly drop this slide and then show you what we achieved and how we achieved. So speaking about the stack size, which we spoke about, let's say running a main thread or idle thread or whatever functionality, the report which says is, yeah, sure. The report shows, wait, maybe I will go to the presentation instead. Yeah, the report shows here is for the kernel. You can imagine 314 bytes is all for the kernel, but eventually that is not the case, because when you realistically invoke some of the kernel service functions, for example, sleep or a mutex lock or a semaphore lock or a spin lock or any form of functionality, that again counts. But in that case, how do you calculate a stack size? So that drops down to the question of puncover and other utilities they've been speaking about. So the trace analyzer and so on. The trace analyzer, if it is a valid choice, we checked. The main reason it is not a valid choice, because the trace analyzer itself needs a 2 kilobyte stack to run to figure out what other stack sizes are. Not an option. So eventually that drops out of the equation. Puncover, when we try to examine this utility for each and every stack size, every prologue and epilogue, it doesn't help because it doesn't report the prologue, it doesn't report the epilogue. Instead, what variables you technically use from an ELF file, but not during an assembly level conditions. So that's when we had to figure each and every bits of it. There is no direct utility to do it with Zephyr, or even there if it is utility, you cannot run on the CPU or because of our limited RAM size. How do you come up with the solution? So the only way is going with the old school. Find the base offset when you get into a function. When you come out of function, figure out how much delta of stack you realistically consumed, figure out how much bytes you went in, and then if you can realistically strip that particular part of the kernel function, strip it. You cannot strip it in, then you are screwed because you cannot run mutex or some respective functions in the scheduler. So that's how it is. We managed to get some good amount of portions where we can run I2Z driver or UART driver of this functionality. I'm not going in detail of every piece of functions, but at least as an example, if you sleep, you need 300 bytes. If you take a mutex, it needs 468 bytes. I can give an example of each and every memory here. That goes beyond interesting stages here. So that's in a nutshell for the presentation. And maybe this is just a recorded video. Let me pull it in. Yeah, so that's like the same compilation which I ran. The main reason we keep a hello world out of the actual hello world is because that is a customer version or customized version, which can technically run in this particular PCB. So that's how we optimized in the management level, and then we're still working on this. Wait a second. Yeah. So there it is reporting the time, which is uptime. Let's say every 1 second in terms of millisecond cycles. So that's we achieved, and also like all the other pieces. I can go detail about each and every sections of what we achieved in the timer driver and how we optimized. But that's how so far we're still gonna work. Yeah, there is this like smallest PCB which we worked in this particular case. I mean, this is also from Texas Instruments. I'm not advertising for Texas Instruments, but so sorry. Yeah, so I have many such things. Okay, so you can ask questions, and to before we close, like we are 5 people from Linux here. We are all work with Linux and Zephyr, so we 5 people travel from Coimbatore for this meetup. So you can feel free to reach us. Ask questions now. Yeah, sure.
I just want to check, you said you replace sustainer with 16-bit timer. Sustainer is 15, 24 bit. What was the conclusion that you saw in the
A good question. So the main reason is like it would if you run at let's say 24 megahertz frequency, the counter would overflow within let's say I think 8 millisecond or something. I forget the math, but with SysTick is 24, whereas this one is like let's say 16-bit. There is also 32-bit timer. That is what we are using. There are two 32-bit timers, and the remaining are 16-bit timers in MSPM0.
Yeah, thank you. I think we have to.
Yeah, go. I mean, one last question. Sorry, Saibal.
So for the combination, you have changed the size to 2 KB.
Yeah.
So have you changed?
Yeah, I changed. I mean, eventually, otherwise it would not run because it is like a memory map device. If you access beyond 1 kilobytes, it would be a crash, but nothing would start at all. Yeah. Thanks so much. I will be available outside if you have questions. We can speak about it. So, thank you.